You've been there. We've all been there, right? You ask your AI assistant a simple question. Something like, what is the primary cause of Earth's seasons? And instead of a straight answer, you get this. The AI just repeats your question back to you. What is the primary cause of Earth's seasons? And then offers you a multiple choice quiz. A, the Earth's distance from the sun. B, the tilt of the Earth's axis. So, why does this happen? This isn't just a bug. It's a fundamental flaw. It's what we call the statistical parrot problem. It's just mimicking patterns without real understanding. But here's the good news. Today, we're going to fix it. We're going to explore the algorithm that revolutionized LLM alignment, Direct Preference Optimization, or DPO. And here it is, the loss function. I know. This equation looks intimidating. But it's the key. And it's built on one incredibly simple and powerful idea you already know intuitively. Judging is easier than creating. Think about it. It's true, right? So here is my promise to you. Give me 1 hour, and you will master direct preference optimization. You will not only know what it does, but why it works, and how to code it. By the end of this video, you will understand every single complexity of it. You'll see how it directly solves the statistical parrot problem, and why it's so much more efficient. So, why did our AI act like a statistical parrot? Let's dig in. A pre-trained large language model knows a truly mind-boggling amount of information, but its only goal, its only motivation, is to predict the next most likely word. That's it. So when you ask a question like, what is the primary cause of Earth's seasons? The model thinks, I've seen thousands of quizzes that start just like this online. It has absolutely no concept of your intent. It's just completing a pattern. So, what's the first solution? It's something called Supervised Fine-Tuning, or SFT for short. And the idea here is really simple. We stop treating the model like a parrot, and we start training it like an apprentice. So how does SFT work? Well, we show it thousands of high-quality examples. We give it data that looks like this. We create a list called training data. Each item has a prompt, like what is the primary cause of Earth's seasons? And then it has an ideal response, something like the primary cause of Earth's seasons is the tilt of the Earth's rotational axis away or toward the sun, and so on. We show it what a perfect answer looks like. This helps us compare the parrot versus the apprentice. Check out this table. On one side, you have the pre-trained model, our parrot. What's its training goal? To predict the next word in any text. Its behavior? It just completes text patterns with no sense of what you actually want. Its key weakness is that it just doesn't know how to be a helpful assistant. Now, look at the SFT model, the apprentice. Its training goal is to imitate expert written responses. Its behavior is to follow instructions and adopt a helpful persona. It's a huge step up, but it has a key weakness. It assumes there is only one perfect answer. This leads us to the SFT limitation. I call it the shades of gray problem. You see, SFT treats alignment as a completely black and white problem. The response in our dataset is treated as 100% correct, and that means any deviation, any at all, is implicitly considered wrong. But life isn't like that, is it? Let's take a simple example. You ask the AI, how do I make coffee? Response A says, add water and coffee. I mean, it's technically correct, but it's super unhelpful, right? Now look at response B. 1. Heat water to 195 to 205 degrees Fahrenheit. 2. Use 2 tablespoons of coffee per 6 ounces of water. 3. Brew for 4 to 5 minutes. And so on. It gives you clear, helpful instructions. As a human, you can instantly state a preference. It takes you half a second. B is obviously better than A. But SFT has no way to learn this relative judgment. It only knows how to copy the one perfect answer it was shown. This brings us to the core insight, the big idea behind modern alignment. It is exponentially easier for a human to judge than it is to create a single perfect response from scratch. Think about it. Creating that perfect response is slow and expensive. But just clicking a button that says B is better, that's fast, it's cheap, and most importantly, it's scalable. So, what if we could build an algorithm that learns directly from these simple preferences? If we could do that, we could align our models more efficiently and effectively than ever before. That algorithm is direct preferred optimization. And here it is, the formula. I know, don't run away. This equation looks intimidating. But this formula is the engine that learns directly from your judgment that B is better than A. And I promise you, we are going to build it together, piece by piece. All right, let's get into it. We've established our core mission. We want to learn directly from human preferences, like the simple judgment, B is better than A. But this presents an immediate challenge, a really big one, actually. How do you convert a discrete preference judgment, a simple this one's better, into a continuous differentiable objective, the kind of objective a neural network can actually learn from? We need a mathematical model. So here's the intuition. Let's call it hidden quality scores. This is the key idea. The core assumption is this. When a human says they prefer response B, they are implicitly telling us that response B has a higher hidden quality score than response A. Think back to our coffee example. Response B, the winner, gave those super detailed instructions. Response A, the loser, just said add water and coffee. So when a human prefers B, what they're really saying is that the score for B, let's call it R sub B, is greater than the score for A, or R sub A. It's that simple. RB is greater than RA. But now we have a problem. From these scores, how can we predict the probability a human would agree with this preference? Let's just invent some scores to make this concrete. Let's say the winner, those detailed coffee instructions, has a score of 2.5, and the loser, add water and coffee, has a score of 0.8. So how do we get from 2.5 and 0.8 to a probability? Enter the Bradley-Terry model. This is the elegant piece of math that solves our problem. So again, our problem is turning scores into probability. We have our scores. The winner is 2.5, the loser is 0.8. Now check out this formula. The probability that the winner is preferred over the loser equals sigma of the winner's score minus the loser's score. R winner and R loser are those hidden quality scores we just talked about. And sigma, what is sigma? That is the sigmoid function, and it's our probability engine. Its only job is to take any number you give it and squash it into a probability between 0 and 1. It's so cool. If you give it a big positive input, the output is super close to 1. If you give it a 0, you get exactly 0.5. And if you give it a big negative input, you get a probability close to 0. Makes perfect sense, right? So let's do the math together. We are going to walk through this entire calculation step by step. Our scores are 2.5 for the winner and 0.8 for the loser. Step 1. Calculate the score difference. We'll call it delta R. We just take the winner's score, 2.5, minus the loser's score, 0.8, and that equals 1.7. Easy enough. Now, step 2. We apply the sigmoid function to that difference. The probability that the winner is preferred is sigma of 1.7. Now the formula for that is 1 over 1 plus e to the negative 1.7, which comes out to approximately 0.845. Now look at this table. This really shows what that score difference tells us. If you have a large positive difference like 5.0, the sigmoid is almost 1. You are almost certain the winner is preferred. Then you have our example, a difference of 1.7. That gives us about 0.845, or an 84.5% chance. We're pretty confident. Now here's the interesting part. What if the difference is 0? That means the scores are identical. The sigmoid of 0 is exactly 0.5, a 50-50 toss-up. The model is completely uncertain. And what if the score difference is negative, like negative 1.7? That means our initial scores were wrong, and the model thinks the loser is actually preferred. So the probability plummets to about 0.155. And just like that, we have converted a simple human preference into a quantifiable probability, 84.5%. We've officially turned a subjective feeling into cold, hard math that a computer can understand. Now we have a probability. But here's the thing. Neural networks require a differentiable loss function to learn. That's how they figure out their mistakes and get better. So the big question is, how do we turn our shiny new probability into a loss function? Well, the standard time-tested method is something called negative log likelihood, or NLL for short. Now, look at this NLL formula. It's actually beautiful in its simplicity. The loss is just the negative logarithm of the probability. That's it. The loss, which we call L, is negative log of the probability that the winner is preferred over the loser. So now we can start building our complete loss function. We just combine the NLL we just learned with our Bradley-Terry formula from before. You can see how we're building our final formula piece by piece. The loss is negative log of sigma of the winner's rating minus the loser's rating. It all fits together. But let's take a quick detour. I know what you're thinking. Why are we using this complicated logarithm? It's a fantastic question. Why not just use something super simple, like loss equals 1 minus the probability? If the probability is 99%, the loss is 1%. If the probability is 10%, the loss is 90%. Seems intuitive, right? Well, let's find out why that's not the best idea. Let's compare the two. Check out this table. We're going to walk through this together. On the left, we have the model's probability. In the middle, our simple loss equals 1 minus p. And on the right, our NLL loss, which is negative log of p. Okay, first row. The model is very confident and correct. It gives a probability of 0.99. The simple loss is tiny, 0.01. And the NLL loss is also tiny, 0.01. So far, they look pretty similar. Next row. The model is totally uncertain. Probability is 50-50, or 0.50. The simple loss is 0.50. The NLL loss is a little bigger at 0.69. Okay, a little different, but not crazy. But now, look closely at the last few rows. This is where it gets interesting. Let's imagine the model is confident and wrong. It gives a probability of just 0.10. The simple loss is 0.90. The NLL loss is 2.30. Ouch, much bigger. Now, what if it's very confident and wrong? A probability of 0.01. The simple loss is 0.99. The NLL loss is 4.61. And the last one, extremely confident and wrong. A probability of 0.001. The simple loss is 0.999, but the NLL loss is 6.91. Let's break that down. With the simple 1 minus p loss, the penalty for being wrong, which was 0.90, and being extremely wrong, which was 0.999, is basically the same. There's not much difference in the punishment. But the NLL loss is different. It explodes towards infinity as the probability approaches 0. It aggressively penalizes being confident and wrong. And what does that do? This creates a much steeper gradient, a much stronger error signal, forcing the model to fix its biggest mistakes first. It's an incredibly effective way to learn. Okay, let's make this real. Problem: calculate the loss for our example. In the last chapter, we found our probability was 0.845. Let's calculate the loss for this single preference pair. It's just 2 simple steps. Step 1. Take the natural logarithm. The log of 0.845 is approximately negative 0.168. Step 2. Negate the result. So the loss is negative of negative 0.168, which equals 0.168. This single number, 0.168, is our inadvert signal for this one preference pair. It's the number that tells the model exactly how wrong it was. And with that, we have now built a complete, self-contained preference modeling engine. We can take abstract scores, turn them into a probability, and then turn that probability into a trainable loss value. We've built the whole thing from the ground up. But there's one big question left. Now, the fundamental question: where do our winner and our loser actually come from? How do we get those scores in the first place? Let's start with our first, most logical attempt. We'll call this the naive approach. It's a great starting point, and it feels really intuitive. The intuition is really simple. A good response is one our model is highly confident in generating. And a bad one is, well, one it's not so sure about. It just makes sense. So how do we measure an LLM's confidence in a specific sentence? We use its sequence log probability. This is a number the model can give us for any chunk of text. This leads us to our first hypothesis for a reward function. Let's call it the naive reward function. The quality score, R, of a response Y, is its total log probability. You can see the formula right here on the slide. R of x comma y equals log of pi sub theta of y given x. Now you might be wondering, what does that actually mean? Well, the probability of an entire sentence is just the probability of the first token times the probability of the second token, and so on and so on. You can see it written out here as a big product. But there's a huge problem with that. Multiplying a bunch of tiny probabilities together, we're talking numbers like 0.001, is a recipe for disaster on a computer. You run into something called numerical underflow. The numbers just get too small to handle. It's a mess. But the beautiful property of logarithms is they turn multiplication into addition, which is so much more stable for a computer to work with. So our naive reward function is back. And now we see the quality score R is the total log probability, but now it's calculated as a stable sum. Check out the formula. The score is just the sum of the log probabilities of each word. Simple as that. Okay, let's make this crystal clear with an example. We're going to calculate a score together, step by step. Let's look at the slide. The prompt X is the capital of France, and the response Y is Paris. Let's calculate the score for this response. First, we look at the log probability of the first token, which is. So what's the log probability of given the prompt the capital of France? Let's say our model gives us a value of -0.2. Okay, step 2. Now we look at the log probability of the second token, Paris. What's the log probability of Paris given the full context now, the capital of France is? Let's say the model spits out -0.3. And for the total score, we just add them up. -0.2 plus -0.3 equals -0.5. That's our quality score. This approach seems perfectly logical, right? I mean, it makes a ton of sense. We just need to train our model to produce a higher log probability, a less negative score for the answers we actually prefer. It feels like we have all the pieces. It seems like we've solved it. Or have we? All right, let's get our hands dirty. In the last chapter, we defined our score as the sum of log probabilities. You can see the formula right here on the slide. The theory is solid. The logic seems perfect. Now, let's do what real engineers do. Let's translate that math into working PyTorch code. Our goal is to create a single robust function, a function that can calculate this score for any given prompt and response. That's the mission. But first, a quick refresher. We need to be crystal clear on how we get from logits to probabilities. When you give a model some input tokens, it spits out raw scores called logits. Check out this little diagram. You've got your input tokens, they go through a model forward pass, and out comes this big logits tensor. The final vector in that tensor has a score for every single word in the dictionary. So let's look at some code. Imagine we have a tiny vocabulary. The is 0, is 1, Paris is 2, and so on. Our model outputs a mock logit vector. Let's say torch.tensor with values 0.1, 3.0, 0.5, and 0.2. The model clearly thinks is at index 1 is the most likely next word. To turn those raw scores into probabilities, we use the softmax function. We call f.softmax on our mock logits with dim equals -1. And bam, we get our probabilities. You can see is now has a probability of over 80%. Now here's the key difference. During normal generation, we would sample from this distribution to pick the next word. But for DPO, we don't need to sample. We already have the response. We just need to find out what probability the model assigned to the words we already know are there. This brings us to the star of the show, the getSequence logprobs function. We are going to walk through this entire thing together, step by step. Don't worry, it's not as scary as it looks. Okay, step 1, combine inputs. First things first, we combined the prompt and the response tokens into one big tensor. We use torch.cat for this. Why? For efficiency. This lets us do a single forward pass through the model, which saves a ton of computation. Step 2. Get logits. This part is simple. We just run our combined input IDs through the model and get our raw predictions, the logits. Easy enough. Step 3. Slice out response logits. Now this is the key trick. This is super important. We don't care about the logits for the prompt part. We only care about the logits that were used to predict the tokens in our response. So we do a very clever slice to grab just those specific logit vectors. Step 4. Calculate log probabilities. With our response logit plants isolated, we can now convert them into log probabilities. We use f.log_softmax for this. Using log softmax directly is much more numerically stable than doing softmax and then taking the log. It's a nice pro tip. Step 5. Gather the right probabilities. This is where the magic happens. We use a powerful function called torch.gather. We have log probabilities for the entire vocabulary at each position, but we only want the probability for the one token that was actually in our response. Gather acts like a super efficient filter, picking out exactly the log probs we need. It's so cool. And finally, step 6. Sum to get the final score. We take all those individual token log probabilities that we just gathered, and we sum them up along the sequence dimension. And that's it. That gives us the total score for the entire response. Okay, I know that was a lot of code. Let's make it crystal clear with a concrete example. Let's score the response is Paris. Look at the slide. Our prompt X is the capital of France, and our response Y is Paris. We'll assume they're tokenized into these tensors. The prompt is a tensor with 1, 2, 3, 4, and the response is a tensor with 5, 6. So in steps 1 through 3, our input IDs become 1, 2, 3, 4, 5, 6. The model outputs light, and then our critical slice, logits 3:5, grabs exactly 2 vectors. The first vector is the prediction from the context France, which is for the token is. The second vector is the prediction from the context France is, for the token Paris. It's so precise. Now let's look at this table to see steps 4 and 5 in action. Let's go really slow here. For the first token is, the context was France. Let's say the model's logits for the words is, Paris, and Lyon were 3.0, 0.5, and 0.2. After we apply log softmax, those become our log probabilities. Negative 0.23, negative 2.73, and so on. Then, the gather function does its thing. It looks at our target token, which is, and it plucks out its specific log prob, negative 0.23. See how that works? Okay, now the second row. The context is now France is, our target token is Paris, the model outputs new logits, maybe 0.1, 4.0, 1.0. It's pretty confident about Paris. The log probs are calculated, and gather once again plucks out the one we need for Paris, which is negative 0.18. And that brings us to the final step, step 6, summing to get the final score. We just add them up. Negative 0.23 plus negative 0.18 equals negative 0.41. That is our final reward score. We've done it. We have successfully built a function that implements our naive reward. It takes a prompt and a response, and it returns a single concrete score. On the surface, this seems perfect. We're ready to go, right? We can get a score for the winning response, get a score for the losing response, plug them into our loss function, and start training. Wrong. We built what seems like a perfect system. We really did. It's simple, it's intuitive, it just feels like it should work. It feels like we should be done. So why isn't this the final solution? Because this system is a catastrophic failure. Let's talk about the problematic reward function. Our naive reward, which is r of xy equals the log pi theta of y given x, creates some unintended and deeply undesirable incentives. It has two subtle but critical flaws. Let's expose them. Failure mode 1, the length bias. Here's the core issue. The log probability of a sequence is a sum of negative numbers. Think about it. Probability is between 0 and 1. The log of any number in that range is always negative. So every single token you add to a sentence makes the total score lower. Let's make this painfully clear with an example. The helpful versus the terse. Our prompt, X, is what is DPO? The human labeler correctly chose the winner, Y sub W, which has 7 tokens, an algorithm for aligning language models. The loser, Y sub L, is just 2 tokens, an algorithm. Now, let's assume we have a confident model where each token's log prob is a nice high negative 0.105. We'll start with the loser. The score for the terse loser, Y sub L, it's just 2 tokens. So that's 2 times negative 0.105, which equals negative 0.21. Okay, pretty simple. Now let's do the score for the helpful winner, Y sub W. This one has 7 tokens, so that's 7 times our negative 0.105, which equals negative 0.735. Okay, let's put those side by side. The score of our relationship winner, R sub W, is negative 0.735. The score of the rejected loser, R sub L, is negative 0.21. Do you see the problem? Our system assigned a higher score to the worse answer. It's a disaster. The model will learn a very clear lesson from this. Shorter is always better. It will become terse and unhelpful, directly fighting the human feedback we're trying to give it. Okay, on to failure mode 2, the bland prior bias. This one is more subtle, but just as damaging. Think of the optimizer like a manager with a limited gradient budget. It's going to spend that budget where it gets the best return on investment. It's just trying to do its job. So, let's look at the optimizer's choice. It has 2 options. Option A is the hard way. It could learn a specific fact, like increasing the log prob of the word Paris from negative 2.0 to negative 1.0. The gain per example is plus 1.0. But this only happens in, say, 10 examples in our whole data set. Now, there's option B, the easy way. It can just polish what's already known. It can nudge the log prob of a super common word like the from negative 0.05 up to negative 0.04. That's a tiny gain, only plus 0.01 per example, but it occurs 50,000 times. So let's calculate the total return on investment. Look at the slide with me. The total gain from option A, learning Paris, is 10 examples times a 1.0 gain per example for a total of plus 10. Not bad. But the total gain from option B, polishing the, is 50,000 examples times a 0.01 gain per example for a total of plus 500. The optimizer gets 50 times more reward for polishing a generic word than it does for learning a useful fact. This leads to a hacked strategy, repetition and filler. The model learns to generate statistically safe garbage to get a high score. It might say something like, "It is a fact that it is a fact that it is a fact that..." Why? Because the log probs of those words are already super high. The score for that hacked response might be negative 0.1, while the score for a nuanced, helpful, human-preferred answer is way down at negative 1.5. The model has hacked our reward function. So, our naive reward is fundamentally broken. Failure 1, the length bias, punishes helpful detail. This leads to short answers. Failure 2, the bland prior bias, rewards statistical safety. This leads to repetitive filler. We need a better way. Our naive reward function crashed and burned. It was a total disaster. It learns to chase statistical safety, calculating the odds, instead of what we actually wanted, which is human preference. The core problem, when you really boil it down, is that we were measuring an absolute score. We were basically asking the model, how good is this response all by itself, in a vacuum? And that was the wrong question. We need to ask a much smarter question. A question that completely reframes the problem. We need to ask, how much better is this response compared to what my model would have said at the beginning of training? See the difference? We need to measure relative improvement, not an absolute score. And to do that, we need a consistent baseline, a measuring stick that never changes. Enter the hero of our story, the reference model. So, what is a reference model? Think of it as a frozen snapshot in time. It is a frozen, read-only copy of our model from the very beginning of DPO training. Okay, let's look at this diagram together to see how this works. This is the DPO training lifecycle. We start with a capable SFT model, right? The one we already fine-tuned. Then, right before DPO training begins, we create two identical copies. One of those copies becomes the policy model. That's pi sub theta. It's trainable, its weights are updated. This is the model that learns. The other copy becomes the reference model. That's pi sub ref. It is frozen. Its weights will never change. Both of these models, the policy and the reference, are then used in the DPO loss calculation to figure out how to update the policy. This brings up a really important question. Why use the SFT model as the reference? Why not just use the original base model that we started with? Because the choice of reference is everything. Let's break this down with the table you see here. First, what if we chose the BBAML? That's a poor choice. Why? Because the base model is just a statistical parrot. It gives you this noisy, meaningless signal from its pre-training. Comparing our helpful assistant to that is, well, it's just a meaningless comparison baseline. Now, look at the SFT model. This is an excellent choice. It provides a strong baseline because it's already a helpful assistant, and crucially, it acts as a guardrail, preventing our model from forgetting all its important SFT training in the hunt for preference scores. So, with our hero, the reference model, in place, we can finally introduce the new DPO reward function. Here's the new rule. The score of a response is the scaled difference between the policy and reference model log probabilities. Okay, check out this formula on the screen. Don't be intimidated, we're going to break it down piece by piece. The reward, R of xy, equals beta times this whole big thing in parentheses. Let's look inside. First, we have log pi sub theta of y given x. That's the score from our trainable policy model. It's what our model thinks now. Next, we subtract log pi sub ref of y given x. That's the score for the same response from our frozen reference model. This is what it used to think. Now, here's the interesting part. The difference between them, that's the magic. This measures relative improvement. A response only gets a high score if our new model likes it a lot more than the old one did. Finally, there's that beta symbol out front. That's just a simple hyperparameter, usually a small number like 0.1. Think of it as a safety brake. It controls how far the policy can stray from the reference. It keeps us grounded. All right, we just introduced our hero, the reference model, pi sub ref, and we crafted a brand new reward based on relative improvement. Here it is again, in all its glory, the DPO reward. The reward R of xy equals beta times the log probability of the policy model minus the log probability of the reference model. Now it's time for the payoff. Let's watch this elegant formula single-handedly solve both of our catastrophic failure modes from before. First up, solving the length bias. Let's do a quick recap of the problem. Our raw log probability reward punished longer responses. Why? Because you're just summing more negative numbers, which always equals a worse score. But here's the DPO fix. The reference model, it has the exact same bias. It's a language model too. So when you're taking the difference between the policy and the reference, the bias just cancels itself out. It's brilliant. Okay, let's rerun the numbers to prove it. We've got our winner, y sub w, that's the good 7-token response, an algorithm for aligning language models. And we have our loser, y sub l, the short 2-token response, an algorithm. And let's set our little safety brake beta to 0.1. Now, let's assume the following log probabilities from our models. Okay, check out this table. We are going to walk through this entire process together, step by step. First, let's look at the top row for our winner, y sub w. Our policy model, log pi sub theta, gives it a score of negative 0.735. The reference model, log pi sub ref, gives it a score of negative 0.750. Now for the DPO reward. We take beta, which is 0.1, and we multiply it by the policy score minus the reference score. So that's 0.1 times negative 0.735 minus negative 0.750. Remember, a double negative becomes a positive, and the result is plus 0.0015. Okay, now let's do the loser, y sub l. The policy gives it a score of negative 0.210. The reference model gives it negative 0.200. So the DPO reward is 0.1 times negative 0.210 minus negative 0.200. That comes out to negative 0.0010. Look at that. The winner's DPO reward is now positive, while the loser's is negative. The reward now correctly signals which response is better, regardless of length. Problem 1, solved. Next up, number 2, solving the bland prior bias. So, the problem recap. Our naive reward gave these huge returns for really common words, encouraging the model to just spit out filler like the, and, is. The DPO fix is just as elegant. Common words are already highly probable for the reference model, PySubref. So the difference, that log pytha th minus log pyref part, is going to be tiny. There's almost no incentive to get better at things you already know. Let's rerun our gradient budget accounting. Okay, let's look at this new table. First row, the generic word the. The policy model gives it a log probability of negative 0.0408. The reference model was already good at this, giving it negative 0.0513. So the DPO reward gain is 0.1 times that tiny difference, which equals a teeny tiny plus 0.00105. Now, let's look at the specific word, Paris. Our policy model gives it a log probability of negative 0.105. But the reference model thought this was pretty unlikely, so its score was way lower, negative 0.916. Now for the reward. We do 0.1 times negative 0.105 minus negative 0.916, which gives us a whopping plus 0.0811. The tables have turned completely. The reward for learning the specific fact, Paris, is now, get this, roughly 77 times greater than for polishing the generic word the. The optimizer's gradient budget will now flow exactly where we want it, towards learning new, useful, and specific information. Problem 2, solved. With 2 elegant strokes, the DPO reward has fixed the fundamental flaws of our naive approach. Our journey is nearing its end. We have battled the statistical parrot, we built a preference engine, we defeated catastrophic failure modes, and we found our hero in the reference model. Now, it's time to assemble the final machine. This is the grand synthesis. Recapping our building blocks. First, we have the preference model. This is the outer shell. It turns scores into a trainable loss. The formula is loss equals negative log of sigma of our winner minus our loser. Second, we have the robust LLM reward. This is the fuel for our engine. It scores a response by measuring its relative improvement. The reward R of x, y equals beta times the log probability from our policy model, minus the log probability from our reference model. Now we perform the final beautiful step. We substitute our LLM reward directly into the preference model. The final formula, step by step. Let's start with the heart of our preference loss, the difference in scores. Our winner minus our loser. The final formula, step by step. Now let's replace our sub-winner with the full DPO reward for the winning response, y sub w. Look at this. It becomes beta times the log probability of the policy for the winner minus the log probability of the reference for the winner. And we still have minus our loser hanging out at the end. And now we do the exact same thing for our sub loser. It's perfectly symmetrical. We replace our sub loser with beta times the log probability of the policy for the loser minus the log probability of the reference for the loser. The final formula, step by step. Okay, this looks a bit messy, so let's just factor out the beta and rearrange things a little. This gives us beta times the difference for the winner minus the difference for the loser. Much cleaner. We're almost there. We just need to plug this entire expression back into the outer shell. The negative log of sigma part. The final DPO loss function. And here it is. The DPO loss is negative log of sigma, of that entire beta expression we just built together. It's all there. This might have looked intimidating at the start, but you now understand every single component. Look here. You know where the negative log of sigma comes from, our preference model. You know where the beta and the reference model terms come from, our robust anti-bias reward. And you know how they all fit together. There is no more magic. We have successfully derived the entire DPO algorithm from first principles, starting from that simple, powerful idea. Judging is easier than creating. We have completed the full theoretical journey. The theory is complete. Now, it's time to translate that theory into a single, working PyTorch function. This is the moment where all the abstract concepts become concrete code. This is the ultimate payoff, the DPO training step. Okay, let's dive right in. Look at this function on screen. This is it. This is the whole thing. We're going to walk through it step by step. The function is called DPO training step. It takes our policy model, our reference model, the optimizer, a batch of data, and of course, beta. Step 1. Get policy log probs. First things first, we need to get the log probabilities from the model we're actually training, the policy model. We call our helper function getSequenceLogProbs for both the chosen and the rejected completions. And here's the key. Gradients will flow through these calculations. This is what we're training. Step 2. Get reference log probs. Next, we do the exact same thing, but for the reference model. But notice this line here, with torch.nograd. We use torch.nograd because the reference model is frozen and doesn't need gradients. This is just a little efficiency trick. It tells PyTorch not to waste time tracking computations for this part. Step 3. Calculate DPO rewards. Now for my favorite part. We get to see our formula in action. We calculate the chosen rewards, which is just beta times the policy log probs minus the reference log probs. And we do the same for the rejected rewards. This is the implementation of our robust, reference-aware reward formula. It's happening! Step 4. Calculate final loss. We're so close. We have our rewards. Now we just plug them into our preference model. You can see it right there. The loss is equal to the negative of f.log sigmoid of the chosen rewards minus the rejected rewards. And we take the mean across the batch. That's it. This is our preference model. Negative log sigmoid of the reward difference. Step 5. Back propagation. And the final piece of the puzzle is pure standard PyTorch. We call loss.backward to calculate all the gradients, and then optimizer.step to update the policy model's weights. And we're done. One training step is complete. A full numerical walkthrough. Okay, theory is one thing, but let's see the numbers. Let's make this real. Problem: trace a single preference pair. Our prompt is capital of France. The chosen response, Y sub W, is Paris. The rejected response, Y sub L, is Lyon. And we'll set our beta to 0.1. Let's see every single number come to life. No more abstractions. Okay, check out this table. Steps 1 and 2, get log probabilities. So we feed our prompt and completions to both models. Let's say for the chosen response is Paris, our policy model gives it a log probability of -10, and the reference model gives it -12. Now for the rejected response is Lyon, the policy model is less sure, giving it -15. The reference model gives it -14. These are our starting numbers. Okay, let's recap. We have our log probs. PyWinner is -10, RefWinner is -12, PyLoser is -15, and RefLoser is -14. And beta is 0.1. Step 3. Calculate DPO rewards. Let's do the math. For the chosen rewards, that's 0.1 times -10 minus -12. -10 plus 12 is 2, so 0.1 times 2 is 0.2. Now for the rejected rewards. That's 0.1 times -15 minus -14. That's -1. So 0.1 times -1 is -0.1. Look at that! A positive reward for the winner, a negative reward for the loser. It's working! We're on the home stretch. Our rewards are chosen equals 0.2 and rejected equals -0.1. Step 4. Calculate final loss. Let's do this in 3 parts. First, the reward difference. That's 0.2 minus -0.1, which gives us 0.3. Second, the log sigmoid. We plug 0.3 into f.log sigmoid, and that comes out to about -0.555. Third, the final loss. We just take the negative of that number, so -0.555 is positive 0.555. That's our loss value. So, our final loss is 0.555. Now for step 5, backpropagation. The optimizer will now adjust the policy model's weights to do 2 things. First, it will try to increase the chosen log PS. For example, it will nudge it from -10.0 towards -9.9. Second, it will try to decrease the rejected log PS. So it'll push it from -15.0 towards -15.1. It's learning the preference. The DPO algorithm in one picture. Look at this summary table. It puts everything we just did in one place. You can see the policy log probs, the reference log probs. Those combine to create our rewards, which gives us our reward difference of 0.3, and our final beautiful loss of 0.555. It all flows together perfectly. We've done it. We have built a complete, robust, and efficient implementation of direct prefractomization. This technique is a cornerstone of modern LLM alignment. It's the engine behind many of the most capable models you use today. You have seen how a simple, practical insight, judging is easier than creating, can be translated into robust mathematics, and finally, into working code. You now understand the algorithm that revolutionized LLM alignment.